Welcome back. I already did a detailed review of that FY6800 function generator from FeelTech, card link, but I received a question about the current, voltage and actual power output, what you can get out of that thing. And the question was specific to a 1 kilohertz sine wave, but I guess we'll do a 1 kilohertz sine wave, square wave, and then a 20 megahertz sine wave and square wave. That's what the oscilloscope is for. If you don't want to see the basics and the math and the measurements, but just the results, feel free to jump to the end of the video using the time index below. Enjoy! Just some quick basics so we are all on the same page. So everybody knows power equals voltage times current. However, that's only true for DC and AC with resistive loads, meaning voltage and current are in phase. And if we're talking about AC power in that context, we also talk about the RMS values of voltage and current. Keep that in mind. If that's no longer true here, we're in a whole different world with real and active power. That's the same actually. Reactive power, complex power and apparent power. So let's stay here with resistive loads and using RMS values whenever I'm saying nothing else for voltage and current. But power is also voltage squared divided by resistance. That's simply your power formula and put in Ohm's law in that form. Or power is equal E squared times resistance. That's again that formula with Ohm's law put in here for voltage. Also, the RMS value for a sine wave is the peak value divided by square root of 2, or the peak-to-peak value divided by, well, trivial 2 times square root of 2. And for a square wave, which we also want to measure, its VRMS is equal to the peak voltage or the peak-to-peak voltage half. Okay, so what are we measuring? So this is our function generator, which includes an ideal AC source, 0.0 blah 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 hertz to 20, 50, whatever megahertz. And this ideal voltage source has a voltage output voltage of V0. Okay, and then we also have that internal resistance or impedance of our function generator, which should be 50 ohms. Okay, now what can we measure? We can measure the output voltage without any load, so no voltage drop here. So we are actually then measuring the V0 voltage without load. Or we can short circuit the whole thing with an ampere meter and we get the short circuit current that thing can deliver. Word of advice, not all voltage sources survive a short circuit. But if we measure both of these values, we can actually calculate the actual internal resistance of the voltage source, which is actually the voltage without load divided by the short circuit current. In either case, we are not measuring any power because either we have, ideally no current flowing if we use a voltmeter, or we have, no voltage drop if we use an ampere meter. So to measure power, we have to connect some load, and we said resistive loads only in this video. And then we can either measure the voltage or the current through our resistive load. We have these formulas here to, calculate the power we get out of that thing. And we should get the maximum power if the external load resistance is matched to the internal impedance. That's the, for solar cells, for example, called the maximum power point. So if these are equal, we should get the maximum power, which is also a way to determine the internal resistance of that thing without, making a short circuit like in that example. Okay, let's get started with the measurements. So, this is future Robert. You will see me again during the video at one point. After I've done all the measurements, and it took a while because, the results I'm getting from this nice signal generator, or let's say from that signal generator, are a wee bit sad. So, better strap in. Let's start with the low frequency 1 kilohertz measurements, and I set the function generator to 20 volts peak to peak here in the display. It's always peak to peak voltage. And 1 kilohertz sine wave, and my multimeter is displaying the RMS value of 7.159 or say 7.16 volts. And if you put the measured value into a calculator, you get a peak-to-peak voltage. We saw the formulas of 20.25 volts. So that value times 2 times square root of 2. So we are spot on. And for a square wave with 20 volts peak to peak, we measure an RMS value of 10 volts. Let's say 10.1 volts. And the formula multiplied that by 2. So we are measuring 20.2 volts peak to peak. Also quite okay for that kind of function generator and that kind of instrument. Now I'm back to the sine wave, but I'm down at the peak-to-peak amplitude to 2 volts, and I'm measuring a short output current of 13.5 milliamps. And so I expect a short circuit current of about 135 milliamps if I go up here to an amplitude of 20 volts peak to peak. Let's see if it survives that. Okay, just for a short time, I will drive up the output voltage to 20 volt peak. 10, 20, and we have 71.21. Okay, something is getting hot in here there, so let's stop that now. Okay, my signal generator survived that ordeal. I'm back at sine wave 20 volts peak to peak, and I'm measuring the output voltage effective, which is still 7.16. So the output stage survived the whole thing, but obviously it didn't like it very much. Something got very hot, and it limited the current. So no short circuiting that function generator here. But anyway, let's try that with a square wave. And for a 2 volt peak to peak square wave, I get an effective current of 19.1 milliamps. And now comes the big moment, 20 volt peak to peak square wave, short circuit current. Okay, same phenomenon, let's switch that off. And I write down the numbers after I reviewed the video. So the unit survived that too, and I'm back at 20 volts peak to peak square wave, and my effective voltage is 10.1 as before, so everything's fine. And I measured an initial current of 86 milliamps, and that was dropping off very fast. Even below 80 milliamps, 70 something. So Yeah, definitely do not short circuit that function generator. Okay. If we have a look at the numbers so far for our set voltage, output voltage of 20 volts peak to peak, our output voltage without load for square wave and sine wave in volts effective was absolutely okay. Things got a little bit troublesome when we short circuit the unit to measure the short circuit current. And we talked about that. But for the initial measurements, and these were going down due to thermal effects, the amplifier stage of the function generator heating up, or maybe the power supply not able to sustain that higher current. The internal resistance we can calculate from that was 97 ohms for the sine waves and 120 ohms for the square wave, of course going up as the current was going down. However, for the 2 volts peak to peak, we got a stable 30.5 milliamps effective and 19.1 milliamps effective for sine and square wave. And that gives us exactly the same internal resistance of that thing. It's output impedance of 52.4 ohms each time in both cases. So not quite 50 ohms, but within plus minus 5% at least. So good enough for that kind of function generator, I guess. Now we are measuring the output voltage with some load, and these two 100 ohm resistors together are spot on 49.0 ohms. And at a sine wave with 20 volts peak to peak, we get an effective output voltage across these resistors of 2.85 volts. Okay, this is future Robert. After that segment, I went into a measurement frenzy, showing you that indeed for 20 volts peak to peak, square wave and sine wave, we get the most power out of the unit when we match the load resistor to the nominal 50 ohms output impedance of the unit. And that went totally awry. So I measured with steadily increasing external load resistance and switching between sine and square wave, 1 kilohertz, 20 volts peak to peak, fully expecting that the output power of the unit would at some point, to be exact 52.4 ohms or 50 ohms nominal, decrease again, but it didn't. And as you saw in the time lapse, I measured a whole lot, and I got up to 97.6 ohms external load resistance, and the power still was going up. I did state in the beginning that the short circuit currents we were measuring at 20 volts peak to peak for square and sine wave are a bit off, and the internal impedance of the unit we calculated from these values were 120 ohms and 97 ohms. And if you take, for example, some square wave with 10 volts peak, which is that square wave here, 10 volts effective is 10 volts peak for a square wave, and divide that by the internal impedance of the unit plus a 50 ohm load connected to the unit, so a total of 100 ohms, that gives you a peak current of 100 milliamps. And as you can see, the unit is not able to deliver that current. So let's reset, okay? We know that the internal resistances we calculated here are bullshit because of the current limitation of our ideal voltage source. And actually I calculated here the internal resistance or impedance of the unit using the ideal VZ voltage. So let's first measure what's really coming out of that unit at set voltage of 2 volt peak to peak. And that's for a sine wave, actually 0.702 volts. And for a square wave, 0.978 volts. So let's say 0.98 volts. And dividing the measured effective voltages divided by the measured effective short circuit currents, we again come to an internal impedance of 51.9 ohms for the sine and 30.3 ohms for the square. Yeah, we're inching closer to the nominal 50 ohms. I guess it's time now to get the oscilloscope out. And just for those of you who are rightfully concerned about probe compensation, I just compensated the probe with the 3.3 volt square wave output of the scope. Yeah, it's connected here. So my function generator is still at 1 kilohertz and 2 volts peak to peak nominal output, but I changed to a triangle wave. As you can see, the reason will be clear in a moment. And it's driving a, well, nominal 50 ohms, so 49 ohm load. I'm always measuring here the effective voltage. And now I'm turning the output voltage up, so peak to peak. 3 volts, 4 volts, 5 volts, everything's fine. 6 volts, 7 volts, 8 volts, 9 volts, 10 volts, everything's fine. 11 volts, can you see something? 12 volts, 13 volts. Yeah, I think you can see it. Yeah, above 10 volts, my triangle doesn't look like a triangle anymore because, well, the unit cannot drive enough current for an external 49 ohm load or a total resistance of 50 ohms nominal, 100 ohms. Let's zoom in. I also displaying the peak-to-peak value and the RMS value of the waveform. Please keep in mind, since we have now a 50 ohmish load externally and the internal impedance of the unit is also 50 ohmish, we have here only half of the peak-to-peak voltage we set at the unit. At the unit we have currently 10 volts peak-to-peak, and I'm ramping that up now, and please have a good look at that triangle wave. So again, 11 volts, you already see it. Doesn't look good, huh? 12, and you see the peak-to-peak voltage is not 6 volts. Okay, 15, yeah, okay, 7, we should have here 7.5, but okay. Let's stop here and go down to 11 volts, but yeah, even there, and I'm in 14-bit mode, so these values are quite accurate. Yeah, no dice. That should be 5.5 volts, but we are already, and you can see it. Yeah. Going into the current limiting. Yeah. And you can see similar effects with the sine wave. So if we go there, up with the voltage, 11 volts, 12, yeah, you can, it's flattening out. And I'm now at 15 volts, so we should have 7.5 volts peak to peak, which of course we don't have. And it doesn't look like a sine wave anymore. So yeah, that's a wee bit disappointing. So, where does that leave us? Are we still friends? I hope so. Anyway, we had a triangle waveform and a load resistor of 49 ohms, and the set voltage on the unit was 10 volts peak to peak. The voltage across our load was 5.03 volts peak to peak, and 1.44 volts effective. And just in case, because I had to add that to my introductory slide, the calculation RMS voltage for triangle waves is peak voltage divided by square root of 3, or peak-to-peak voltage divided by 2 times, of course, square root of 3. Anyway, and all at 1 kilohertz low frequency. So, using Ohm's law, we can calculate that our maximum load current was 51 milliamps peak, and that leaves us, again, Ohm's law, do your own calculations, with a maximum power of 128 milliwatts. And the minimum load you connect to the unit depends on minimum load resistance, depends on your set voltage peak to peak. And it's, the set voltage peak to peak times 0.5. So, just peak voltage divided, Ohm's law again, by our maximum current the unit can provide. And of course, minus the already internal impedance resistance that is there. Or, with numbers, we set peak to peak times 0.5 divided by our 51 milliamps peak minus 50 ohms. Let's test that. This time I have a 100 ohm nominal, well, it measured at 98 ohms load resistor, and we start at 10 volts and go up and see what happens. So 11, 12, 13 still looks good. 14, 15, I have to scale down a little bit. 15 volts, you see what? So 14 volts, okay, 15 volts, So we measured a triangle waveform at 1 kilohertz, and the highest we said we could achieve without distortion of the signal was 14 volts peak to peak with a load resistance of 98 ohms. And we measured a peak-to-peak voltage of 9.4 volts across the load, or 2.7 volts effective, which gives us a peak current through the load of only 48 milliamps peak. And side note here in between, if that would have been a square wave, we would have gotten out 225 milliwatts out of the unit into the load. Well, the formula I developed only a few cuts ago obviously doesn't work. So for 14 volts peak to peak, we should have been able to use a minimum load resistance, 14 volt peaks to peak, times 0.5 divided by our 51 milliamps maximum current minus 50 ohms internal impedance. That is minimum external load 87 ohms. And for 15 volts, it would have been 97 ohms. So with external resistor of 98 ohms, we would have to expect it to see a nice waveform at 15 volts peak to peak, which we did not, because obviously at these higher output voltages, the output stage starts to crush the signal at 48 milliamps peak. Okay, next step, let's try to get let's say 20 volts out of that thing without any distortions. That is, we set 20 volts peak to peak without any signal distortions of our triangle wave. And using again our formula, but this time with only 48 milliamps peak maximum current, we get a load resistance of minimum load resistance of 158 ohms. So let's try to do that with 160 ohms. Okay, this is really getting ridiculous. I'm, again, triangle 15 volts currently, and 16 volts is okay, but 17 volts distorted signal. We are at the end of the ladder with a 158, it measures in at 158 ohms load resistor. So again, 15 volts, 16 volts, okay, 70 volts, distortion. Yeah. Okay, I didn't film a step in between with a 197 ohm resistor, a nominal 200 ohm, which brought me up to 17 volt peak to peak set voltage. And now I have a 295 ohm load resistor here, nominal 300 ohms, and I'm at 19 volts. And if I go to 20 volts, you probably can see it here. I'll zoom it in anyway. So 19 volts, look at this here, and 20 volts. I tried a 330 ohm nominal load resistor here for 20 volts peak to peak, and it didn't work out. And I'm now up to a 360 ohm nominal, which measures in at 354 ohms. And we finally have a undistorted triangle wave. At 20 volts peak to peak set voltage. So these were all the measurements I took, and we started out with a 98 ohm resistor, which should have yielded us easily 15 volts peak to peak set voltage undistorted signal, but it didn't work out because at 14 volts peak to peak set voltage the unit can only deliver 48 milliamps. And this trend now continued up to set voltage of 20 volts peak to peak. And I had to use a load resistor of 354 ohms to get an undistorted triangle signal out of that thing. And that means the maximum current delivered at set voltage 20 volt peak peak is 25 milliamps peak. Okay. Now, what does that mean for high frequency stuff? What does that all mean for high frequency? When you're working with high frequency, you have two options. Either, when you have a 50 ohm impedance source, you use a 50 ohm BNC cable, and at your end you have a 50 ohm terminator. That is, you put a 50 ohm load, external load, as we have before with resistors at 1 kilohertz, on your unit. But we already know that we can drive an external 50 ohm load only up to a set voltage of 10 volts peak to peak. And I have here a 20 megahertz sine wave with a set voltage of 20 volts peak to peak, and it doesn't look like a sine wave. We really have to dial down the set voltage to 10 volts peak to peak so we get a nice sine wave, because the output stage cannot drive a 50 ohm load at above 10 volts peak to peak. We also see here that the voltage that is going into the oscilloscope is only 3.8 volts and not 5 volts peak to peak as it should be with above here 10 volts peak to peak set, 50 ohms output impedance and 50 ohms termination. So voltage divider 1 to 1. We should here have 5 volts. But this is just within, the industry accepted 3 dB dampening, which would be about 3.5 volts. But anyway, let's see how far I have to turn down the frequency so we actually get here 5 volts peak to peak. And now I'm turning down the frequency and we get 0. I have to turn down the scale here, 0 dB dampening, and the other scale for 10 volt output let's be generous at 4 megahertz. At 5 megahertz, not quite. So at 4 megahertz. Let me do the measurements, and I will do it for amplitude of, for all amplitudes, for all 10. It's only 10 measurements. Give me a sec. That's what I measured. Okay. So all with 50 ohm termination, and as we increase our VZ voltage on the unit between 1 and 10 volts in 1 volt steps, the frequency at which we really measure half the set voltage, 50 ohms internal impedance, 50 ohm termination, voltage divider, it decreases. It starts at 10 megahertz for 1 volts peak to peak, and then it falls off at 4 volts to 7 volts peak to peak to 4 megahertz, and then it stays at 4 megahertz. I said the first way to get the signals out of here is a BNC cable with a 50 ohm terminator. The second way is, of course, to connect a high impedance oscilloscope probe directly. And we can do the same measurements here. In this case, we can actually use a set voltage of 20 volts peak to peak because, we're not drawing any significant current out of the unit. And you see, I have 20 volts here, and at 9 megahertz, I get a nice sine wave with a peak to peak voltage of exactly 20 volts peak to peak. But if I increase the frequency, my peak to peak voltage drops. So I will do the same here and see where I get 0 dB dampening from the output stage of the function generator. Be back in a sec. When we connect high impedance oscilloscope probes directly to the unit, we see another picture. As we increase the VZ voltage on the unit, the frequency where we actually get exactly the VZ voltage out, so 0 dB dampening from the output stage or whatever within the function generator, we start at 13 megahertz at 2 volts peak to peak, and that quickly drops off to 9 megahertz at 6 volts peak to peak set voltage. And remember, here at 5 volts, the relay makes a click, so something changes inside the unit, and then it stays pretty constant up to 20 volts peak to peak, which we can utilize because we are not drawing any current out of the unit, and 9 megahertz. To summarize, and please take the values I show here with a little grain of salt. I didn't do precision measurements, so let's say plus minus 5% or something like that. Anyway, for low frequencies, and I did all measurements at 1 kilohertz, the unit can supply a maximum output current of 50 milliamps peak, up to 10 volts. If you increase your set voltage, which is in peak to peak in the unit, above 10 volts, the current the unit can supply drops down. It drops down to about-ish 52 milliamps at 20 volt VZ. And yeah, 19 volts, 28 milliamps, and so on. It's pretty linear up to 14 volts, we said, where we have 48 milliamps. Meaning up to 10 volts, we set peak to peak, you can actually connect a 50 ohm load. But if you go above 10 volts, we said, you have to increase your load resistance until you end up at 20 volts, we said, with a minimum load resistance of 350 ohms. And yeah, that gives you an output power of about 220 milliwatts. And yeah, here at 10 volts with a 50 ohm load, you get an output power of about 125 milliwatts. For high frequency, either with a 50 ohm termination, that is connecting the unit via BNC cable with a 50 ohm terminator to something, or high impedance, for example, directly connecting oscilloscope probes to the unit, I measured the frequency at which we have zero attenuation inside the unit. So yeah, frequency for 0 dB attenuation versus the set voltage on the unit. And if you use 50 ohm termination, yeah, the end of the line is naturally here 10 volts peak to peak, because it can only drive 50 milliamps. And if you go beyond 10 volts set voltage peak to peak, yeah, you would need more than 50 milliamps, and the unit cannot provide that. So for 50 ohm termination, we only look at the range between 1 and 10 volts, we set. And there we have, yeah, starting at 1 volts, we set peak to peak. We can get out a 10 megahertz sine wave without any attenuation. Yeah, not attenuation again in the oscilloscope, but in the unit itself. And that holds up until we are at 3 megahertz and 3 volts peak to peak. And then it drops down to 4 megahertz. We can set the unit to and exactly get the voltage out we expect. For high impedance, it looks a little bit better. We are not drawing any current out of the unit, so we can actually go up to 20 volts set voltage peak to peak. And here I only obviously measured in 2 volt steps at 2 volts set voltage. We can have a 13 megahertz sine wave without any attenuation, and that quickly drops down at 6 volts peak to peak set voltage to 9 megahertz. We can get out of that unit without any attenuation, and that stays pretty constant up to 20 volts set voltage. To be fair, in all measurements, I checked that. So up to 60 megahertz sine wave, the attenuation is better than the industry standard of minus 3 dBs. But yeah. The question is, why? And the answer is probably quite simple. That unit here, the FY6800 from FeelTech, or yeah, their clones, they go currently for about $75 at Banggood. A good line driver, let's say with a bandwidth of 200 megahertz and able to drive up to 100 milliamps, costs, if you buy them by the thousands, yeah, $1 or $2. You need 2 of them because you have 2 channels, and yeah, just for $2 to $4 BOM cost, plus yeah, you need some passives around them. That's probably too much for a really good output stage in such a cheap signal generator. Yeah, well, you have to live with it. if you know the limitations of that thing, it helps to prevent any surprises when you using that unit to do actual precision measurements. You just have to stay inside, accept it's a cheap unit and stay inside its limitations. This video has gotten much longer than I expected, and it's all the fault of the viewer who asked that question. What's the maximum current you can get out of the thing? And I thought, easy answer, just do a measurement and be done with it. But characterizing a crappy output state with all its limitation of a cheap function generator is, turned out it's not as easy. Anyway, I hope this video helps you to use your FY6800 a little bit better and get over any disappointments you might have experienced with the unit. Anyway, until next time, bye.